In this video, we will be covering how to solve differential equations using the separation of variables solution technique. So first, let's cover what a separable differential equation is. A separable DE is a DE that can be written as your derivative y prime or dy dx is equal to a function of x times a function of y. So you can't have a sum of functions in terms of x and y. That's a different kind of object entirely. It needs to be specifically a product. Okay, so that is what a separable differential equation is, and it's going to be essentially our only form of differential equation that we will be solving in this class, but in future classes, you'll learn more solution techniques for different kinds of differential equations. So first, we're going to find the general solution to the differential equation dy dx is equal to x squared minus 4 times 3y plus 2. So the first thing for solving a separable differential equation is to do exactly that, which is separate your variables. So I'm going to highlight the function of x and highlight the function of y. Super easy to see with the parentheses. And then we're going to move all the x's to one side, and it's going to be the right side because if I multiply by dx, I can get the dx on the right. So I always recommend rewriting your y prime as a dy over dx because the notation lends itself really well to this solution technique. So I multiply both sides by dx. I get dy equals x squared minus 4 times 3y plus 2 times dx. Now I'm going to move the y function out. So divide both sides by 3y plus 2. And I get 1 over 3y plus 2 times dy equals x squared minus 4 times dx. Okay, now we'll see in a second why I chose to write the left-hand side the way I did, because what are we going to do to both sides? We have a function of y and a differential in terms of y, a function of x and a differential in terms of x. If we integrate both sides, we can get rid of the differentials and get functions in terms of y and x. And let's take a look what they look like. So it looks like the left-hand side looks vaguely like a logarithm is involved. It looks like it would basically be ln of 3y plus 2, and then we need our correction factor for a u sub. So I'm thinking that if we multiply times, let's see, it would be 3 needs to be present for the derivative, so we'd multiply by a third. We'd end up getting a third ln of 3y plus 2 for the left-hand side. And for the right-hand side, we got a power rule, 1/3 x cubed minus 4x. And go ahead and put the integration constant. I always tend to do it on the right side. So just pick a side and put an integration constant down because there will be one present when we do this. Okay, now if we're looking for what's known as an explicit solution, like technically this is a solution to the differential equation, but it's not considered explicit because the left-hand side, like we don't have y equals, we have a function of y. So to take this one step further, this is called an implicit solution, and it's still general. Okay, this is an implicit solution. If we wanted to get an explicit solution, we would have to go one step further and do some more algebra on this. So I would have to multiply both sides by 3. I'd get ln of 3y plus 2 is equal to 3 times a third, so that would be just x cubed minus 12x plus 3c. I'm going to wait to rename this constant for a while here. Then I'm going to raise both sides as the power of e. So I get absolute value of 3y plus 2 is equal to e to the x cubed times e to the negative 12x times e to the 3c. Okay, and right now it's going to seem like, well, why would you split up the right-hand side using exponent rules? The reason I'm doing this is because I have a constant, e to the 3c. That's just going to be a number. So I am going to choose to rename this, and we're going to call this a new constant, d. So we'll call this d. Okay, so now if I want to drop the absolute value bars, I need to use the fact that it could be plus or minus, and it's going to depend on the initial condition. So this is 3y plus 2 is equal to plus or minus d e to the x cubed. I can guess I can put those back together now. Minus 12x. And then subtracting 2 from both sides, I have 3y is equal to plus or minus de to the x cubed minus 12x minus 2. Dividing both sides by 3 finally gives me my final solution. So y is equal to, and a lot of people would argue that we shouldn't really leave a plus or minus d over 3 for a coefficient because that's just kind of not very clean way to write it. We could rename this as another letter. We could call it like capital F or something if we wanted to, and then use our initial condition to solve. That's fine. So we could call it e or f e to the x cubed minus 12x minus 2/3. There we go. So there is our solution here. This is considered our explicit solution. And we'll still have that constant f because it's not an initial value problem, so we don't have enough information to solve for what f would be. Okay, let's take a look at another example. So for our next example, we're going to use the method of separation of variables to solve dy dx is equal to 2x plus 3 times y squared minus 4. And our initial condition is y of 0 equals negative 3. Okay, so to get started here, we're going to separate our function of x and our function of y again. For the left-hand side, hopefully it's a little more obvious now that we saw the algebra in the last example that our left-hand side will be 1 over y squared minus 4 times dy. And our left-hand side will be 2x plus 3 times dx. And I can then integrate both sides. Okay, so this time the left-hand side is a little more interesting for the integration. We don't want to rush this. This is kind of like having the integral of 1 over y minus 2 times y plus 2. And hopefully we're remembering our integration techniques for how we can handle an integral like that. Basically what we're going to do is partial fractions decomposition. It looks like a perfect example of where that strategy would lend itself particularly well. So the partial fractions on this ends up being integral of 1 over 4 times y minus 2 minus, or we could just view it as plus, negative 1/4 y plus 2. And to confirm this, you would do partial fractions decomposition. So if you need a refresher, maybe you're stopping into these videos not in linear order, but if you need a refresher on how to do partial fraction decomposition, I have two different videos where I do both integrating with partial fractions decomp and then another video where I just do the partial fractions decomp with no integration that I will link. Okay, so now we can go ahead and integrate. We end up getting that we get 1/4 times, and we have a 1/4 factor for both integrals on the left, so we can just factor that out. This would be ln of y minus 2 minus ln of y plus 2 for the left-hand side. And for the right-hand side, we get x squared plus 3x plus our integration constant. So remember, I always like to do it on the right. Sometimes if you put it on one side, you can make your algebra harder than if you put it on the other side. So I think generally the side with x's tends to be the easier one, I think. And I'm kind of saying right because that's where I've been putting the x's. But yes, that's where I think the integration constant is the easiest to work with. Not saying that it's the only way to do it. Okay, so if we go ahead and multiply both sides by 4, we get 4x squared plus 12x plus 4c is equal to ln of y minus 2 minus ln of y plus 2. And this is where I really love the algebra of this, just because I teach a lot of pre-calc, really like pre-calc. It reminds me very much of our log rules section because I have an equation that's really hard to solve for y. This would be considered an implicit solution because my y is not solved for by itself. It's not isolated. So this is considered an explicit solution, and oftentimes this is an implicit solution, and oftentimes we want an explicit solution. Okay, so this is an implicit solution, and I want to isolate y. How do I do that? Using my log rules, of course. This would be y minus 2 over y plus 2 to condense that. And then my right-hand side would be 4x squared plus 12x plus 4c. And then I can raise both sides to the power of e, and we get the absolute value of y minus 2 over y plus 2 equal to e to the 4x squared plus 12x times e to the 4c. I'm kind of isolating out that constant term, and I'm going to choose to rename this as d in this point of time. So I get d e to the 4x squared plus 12x, and then I get y minus 2 over y plus 2. And ooh, this one, the algebra is gonna get spicy. We're gonna need another page. I can already see the future here. Okay. So when I change this to a d, I will drop the absolute value bars and get y minus 2 over y plus 2 equal to, we'll call it d e to the 4x squared plus 12x. Let's not call it d at this stage. I'm just going to be kind of do this all at once. So technically, when you kind of rename variables, I should have came up with another variable name, but I didn't want to. So I just kind of did the renaming and dropping the absolute value all at once to make it a little cleaner and not have to do another variable renaming. Okay, so now I'm going to multiply both sides by y plus 2. So on the left-hand side, I have y minus 2 equal to d e to the 4x squared plus 12x times y plus 2. And I can tell it's going to get interesting because I'm going to have to then distribute my function of x to both terms, and then I'll have two terms that have a y. So y minus 2 equals d e to the 4x squared plus 12x times y plus 2d e to the 4x squared plus 12x. And remembering how to algebra, right? How to solve this algebraically. I have a y term on the right side, and I have a y term on the left side. I need them on the same side as each other. So I'm going to go ahead and subtract we'll put the y's on the left. So I have y minus d e to the 4x squared plus 12x times y. And I'm going to add the 2 to both sides. So I get 2d e to the 4x squared plus 12x plus 2. So I'm kind of putting all the y's on one side, all the x's on the other side. And now I have a common factor of y that I can factor out on the left. So I factor my y out, and I'm left with 1 minus d e to the 4x squared plus 12x. And then on my right-hand side, I have 2d e to the 4x squared plus 12x plus 2. And I'm going to be careful here, and I'm not going to just rename this 2D something else because I'm referring to D on the left-hand side now as well. So I'm going to leave these as D's even if it doesn't look quite as nice and divide both sides through by 1 minus D e to the 4x squared plus 12x. 1 minus D e to the 4x squared plus 12x. So my y, my explicit solution, we're finally there, is 2D e to the 4x squared plus 12x plus 2 over 1 minus D e to the 4x squared plus 12x. Okay, doesn't look pretty, but I mean, there it is, right? So this is our general solution. Okay, it's general because we have not solved for our constants yet, but we were given an initial condition. Okay, so with the initial condition, I should be able to solve for what D is equal to. We'll see. We'll see. So there's two different ways to go about this. If you are given an initial condition, you are allowed to plug it into any step of your solution that you want. So it might be easier to plug into the explicit solution for y. Okay, so like I might want to plug in, I might want to plug in here. You also have the right to plug in to your implicit solution. So maybe I want to plug in over here. So if my y is 3 and my x is 0, in this problem, I don't really see one way being significantly easier than the other, but maybe the way with less ln's is what most people would choose. Maybe they would plug into the general solution, so I'll go about it that way. So if y of 0 is 3, then 3 should be equal to 2d e to the 0 plus 0 plus 2 over 1 minus d e to the 0 plus 0. So I get equals 2d plus 2 over 1 minus d is 3. So that tells me that 3 times 1 minus d equals 2d plus 2. 3 minus 3d equals 2d plus 2. So 5d is equal to 1. D is equal to a fifth. Oh, shoot. Y of 0 equals 3 or y of 0 equals negative 3, right? That's going to change things. Sorry, we should change that. So now that we have our general solution, we need to use our initial condition, which is that y of 0 equals negative 3. So if y of 0 is negative 3, I can go ahead and plug in negative 3 is equal to 2d times e to the 0 plus 2 over 1 minus d times e to the 0. So I get negative 3 equals 2d plus 2 over 1 minus d. So I get negative 3 times 1 minus d is equal to 2d plus 2. And that distributes as negative 3 plus 3d equal to 2d plus 2. And putting all of my variables on one side, numbers on the other, I get that 5. Looks like I get 1d is equal to 5. So substituting that into our solution, we get y equals 10e to the 4x squared (10e to the 4x squared plus 12x plus 2 all over 1 minus d was 5e to the 4x squared plus 12x. Okay, so bearing that in mind, there is our particular solution. Okay. And that's truly as far as we can go. We've used our initial conditions, and that's the end. So in our next video, we will cover a common application of solving separable equations, which is Newton's law of heating and cooling. So I will see you in that video.